Hi, my name is Ubaldo Reyes. We are in my office at the Centro Estatal de Cancerología Durango in Mexico. In this video, I'm going to show you how to understand the gamma index in radiotherapy.
Content. The content of this presentation is the following. We'll provide an introduction, we'll state our problem, we'll answer the problem, and we'll provide an example. At the end, we'll comment on this subject. Introduction. The gamma index is a technique that allows us to compare two dose distributions, a measured one and a calculated one. Problem statement. Have in mind a measured dose distribution, and we'll compare it with a calculated dose distribution. The measured dose distribution is an array of instruments that measure radiation. They can be ionization chambers, diodes, and many other instruments. The calculated dose distribution is a plain dose that's generated by a planning system. Our question now is, how do we compare the two dose planes? Solution to the problem. To give this issue a solution, let's have in mind a coordinated tridimensional system with axes x, y, and z. The axes x and y form a plane. On that plane, we have each and every one of our radiation detectors. Suppose that every detector has a position on that plane, xm and ym, and evidently it also has a position vector rm. Around this point, we generate an ellipsoid of revolution, which its equation is the following, where we have xm, ym are the spatial coordinates of each detector. And there's two characters, delta and d. Delta is the ratio value of the circumference generated on the plane xy. And d is a difference of dose in percentage. Both values are determined by us. Delta could be 1 millimeter, 2 millimeters, or any value. And d could be 1%, 2%, or any value. They're character values of our ellipsoid of revolution. Let's think of a point, PC, which is a point of the plane dose calculated by the system of planning. This point evidently on the plane x and y has coordinates xc, yc, and a position vector rc. The value zc is a difference of dose, and it could be compared in a local manner, which has to do with the comparisons of dose calculated on that point against the measured dose by the detector. What we're saying is that we're normalizing in a local manner, but we can make a normalization to any other point. For example, we could normalize the maximum value of dose registered in our detector array. Now we'll make a mapping of all the coordinate points x, y that are within the surface enclosed by the circumference of delta radio. For that, we'll clear out z from the equation. But now we'll determine the value x, y in all coordinate points x, c, y, c from the planning system. So z prime is valued as all absolute value of r less than or equal to delta, where we know that vector r is the difference between the position vector calculated minus the position vector measured. Now we ask ourselves, how do we know that the coordinate points PC is inside of the volume enclosed by our generated revolution ellipsoid. PC will be within the enclosed volume by that surface only if the absolute value of ZC is less than or equal to the absolute value of prime Z, for every absolute value of R less than or equal to delta. Now, we have this inequality, and it still complies if the quotient divided is less than or equal to 1. ZC is a value we know Z prime is given by the equation we already saw. We define the gamma uppercase function as the quotient of the absolute value of ZC over the absolute value of Z prime. We define the function gamma uppercase 1 as the minimum of the function gamma uppercase defined previously. For every position vector of the coordinate points calculated by the system planning, if gamma uppercase 1 is less than or equal to 1, then we generate pi, which would be 1. And in any other case, pi would be equal to 0. Finally, we define gamma, which depends of two parameters, the ratio of our circumference and the height of our revolution ellipsoid. And what we do is add all the positive points 1, and we divide it within the total number of detectors. And finally, we multiply by 100. And that's what we report as our gamma value. In summary, every detector that measures radiation, we know its position and we show it on the plane XY. As I said, we have coordinate points 1 or 2 and point N. They're the detectors that measure radiation that we would have around every single one of them generate a revolution ellipsoid with the character delta and D, which equation is as demonstrated. We also have our calculated plane, those generated by a planning system. What we're going to do is look within every ellipsoid if there's at least one coordinate point of the planning system that's within the ellipsoid of revolutions generated. If there's a point, we have 1, and if there's none, we have 0. We add all of them, we divide by the total number of detectors, and then we multiply by 100. Example. Let's give an example in the State Center of Cancerology. We have the tomotherapy equipment, HDA, and we have the array of detectors, ArchCheck, which has around 1,300 diodes that are located in a cylinder form. After making a quality control of specific patients, we have this report on the right side. We have the plane calculated dose by the planning system, and on the left side, we have the plane measured dose, and let's take a look at the results. Number of detectors, 1,087. We didn't utilize 1,300 because of the line base that was used. They passed 1,086 tests, and the one that didn't pass was only 1. Delta, which is known as distance to agreement or DTA, was 3 millimeters, and the height of our ellipsoid was 3%. The final result would be written like this: gamma 33 equals to 99.9%.
The gamma index is a mathematical tool that helps us compare to those plants. The most important is understand it from its most basic form to be able to apply it adequately in each of radiotherapy centers. I hope this video is useful for you, and well, see you in the next.